Now we're going to extend the idea of similar triangles and apply it to a very specific scenario of right angle triangle, and we're going to discover something called the trigonometric ratios. So first start by drawing any right angle triangle of any dimension. So I highly encourage you to do this exercise along with me. Using a ruler, you measure the three sides, AB, BC, and AC. Here I have AB is 3.7, BC is 4.6, and AC is 6.0. You will probably have different values. Now when you compute these ratios, you can compute 6 ratios because there are 3 sides. You can have AB divided by BC, or the opposite, BC divided by AB. You can have AB divided by AC, or the opposite, AC divided by AB. And you can have BC divided by AC and its opposite, which is AC divided by BC. And then you end up with these ratios. Now you can make a bigger triangle using similar dimension, meaning you just extend this part A to D and part E to B. Now in this big triangle, repeat the procedure. Find the ratio of DEEC, ECCD, and DEDC. What will you notice? Well, if you did everything correctly, you will find that the ratios are exactly the same for the small triangle and the big triangle. They shouldn't come as a surprise because they are similar. This means that for all of the following triangles, the black, the pink, the purple, the blue, the green, the ratio AB over BC equals the ratio DE over EC equals the ratio FG over GC equals the ratio HI over IC equals the ratio JK over KC. Now what's common to all of these triangles? That's the angle right here at C. So what this tells us is that for a fixed angle, the ratio of the sides of a right triangle are equal. Now these ratios, we give them a name, and these are called trigonometric ratios. And all the 6 possible ratios have a special name. Before proceeding, let's establish some terminology. We have often used small letters X, Y, Z, A, B, C as variable names for things like length or maybe volumes or areas. Now for angles, we use the Greek letter theta as like a zero with a belt. The 6 possible ratios are AB over BC. AC over BC, that's called tangent. The reciprocal, or the opposite of that, BC over AC, is called the cotangent. AC over AB is called sine. AB over AC is called cosecant. BC over AB is called cosine. And AB over BC is called secant. In short, we write sine theta, cosine theta, tan theta, CSC theta, secant theta, and cotangent theta, or cot theta. To assist in remembering, you can use the following method. Now in the triangle, we already know that the longest side is called the hypotenuse. If you're working with this angle theta, and looking from theta, there's a side that is exactly opposite to it. We call that opposite. And the remaining side is right next to theta, is called adjacent. So you can say sine theta is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. And if you look at the first letters, you can form the acronym SOHCAHTOA. So sine, opposite hypotenuse, cosine, adjacent hypotenuse, tangent, opposite adjacent. So that's one way to remember this information. Moving on, example. Let's say you're given a right triangle with the sides 3, 4, and 5. Five is the hypotenuse. With respect to theta, the opposite is 3, and the adjacent is 4. The sine theta is opposite over hypotenuse, which is 3 over 5, or 0.6. Cosine theta is adjacent over hypotenuse, 0.8. And tangent is 3 over 4, which is 0.75. Now, if you compare the definition, you will find this relation that cosecant theta is 1 over sine theta, secant theta is 1 over cosine theta, and cotangent theta is 1 over tangent theta. So here, since we've already found sine, cosine, and tangent, we can find cosecant theta as 1 divided by 3/5, which is 5/3. Secant theta is 1 divided by 4/5, which is 5/4. And cotangent theta is 1 divided by 3/4, which is 4/3. Now let's look at another example. Here, theta, here you have to be careful, is not the angle that we have been marking before. It's the other angle. So now The opposite with respect to this theta is the one that's at the bottom, and the adjacent is the one that's vertical. So the value of sine, cosine, and tangent changes accordingly. Now, recall that we learned something called the Pythagoras theorem for a right triangle. Now, sometimes you may have to apply Pythagoras theorem to find trig ratios. For example, if you're given this triangle with hypotenuse 25 and one of the legs 7, and you're asked to find tan, cosine, and sine. First, you are going to have to apply the Pythagoras theorem to find the unknown side. So a squared plus b squared is c squared. Solving gives you a is 24. So sine theta becomes opposite, which is 7, over hypotenuse, which is 25. Cosine is adjacent, which is 24, as you just found out, divided by hypotenuse, which is 25. And tangent is opposite, which is 7, divided by adjacent, which is 24. Another type of problem is if you are given one of the ratios, you may be asked to find the other. For example, tangent theta is 1, find sine theta. Now, any number can be written as a fraction just by dividing it by 1. So here I can write tangent theta as 1 divided by 1. But I also know that the definition of tangent is opposite over adjacent. So we make a triangle with the opposite being 1 and the adjacent also being 1. We can find the hypotenuse using the Pythagoras theorem as x squared equals 1 squared plus 1 squared, giving me x is square root of 2. So sine theta, which is opposite over hypotenuse, becomes 1 over square root of